Okay, in this, I've got a moment applied to a beam that has a cross-section of a triangle as shown here. And I want to figure out what the largest moment so that I don't exceed a tensile stress of 22 KSI and a compressive stress of 15 KSI. So the first thing I need to do in this problem is find the centroid of the cross-sectional area, which again is going to be 1/3 of the height of a triangle. So I have 1/3, and then this is the height from Pythagorean theorem, which is the hypotenuse is 4, one side is 2, so to find the other side I just take the square root of the difference squared, and I get the centroid is at 1.15 inches up from the base. So that'll tell me where that neutral axis is located. Now I want to find the moment of inertia about that neutral axis, which for a triangle is 1/36 times base times height cubed. So I have 1/36. My base is 4, and my height again is from the Pythagorean theorem cubed, which gives me 4.6 inches to the 4th. That's my area moment of inertia about the neutral axis. Okay, so now I'm going to look at the tensile load, and tension is occurring on the bottom of this. The bottom is stretching, the top is compressing. Okay, so on the base of my beam here, okay, I can't exceed 22 in tension, so I take my moment that I'm looking for times the distance from the neutral axis to the base, which again is 1.15, divided by the area moment of inertia, and I find that the moment that that I don't want to exceed will be 7.33 kip feet. Okay, doing the same thing for compression, this time it's 15, and the distance is the total height, which is this 3.46, minus the location of the centroid, 1.15. So again, that's the height from the neutral axis up to the top where the compression is occurring. I is the same. Calculating M so that it doesn't exceed 15, M is actually 2.5 kip feet. So this is actually the answer because I do not want to exceed that. If I exceed that, then I will exceed the 15 KSI, even though I won't exceed the 22 KSI in tension. Okay, so when doing this, you have to consider both the top and the bottom compression and tension, figure it out using the Flexure formula accordingly.